Right.
Okay. Well, so I guess the goal for today, I mean, maybe recap a little bit about what Guan Yu talked about on Tuesday. So last time we defined this category of motivic spaces, um, and the way that Guan Yu defined this is this was the category of simplicial presheaves on smooth schemes, uh, or pointed simplicial presheaves. And this is what we called motivic spaces. And uh, what Guan Yu did was so last time we gave this a model structure, which I think we called the local structure. And the maybe the basic idea of this is this up to homotopy, these things should be uh, like these Nisnevich sheaves. And we kind of just force the fibrid objects so that we have A1 contractibility. So this was a really like kind of hands-on way of working with these things, and it was pretty low tech, and it didn't require too much fancy machinery or uh, anyway. It was but the rest of the text we've been following takes a different approach to defining these motivic spaces, and so my goal, so the goal for today is to define uh, these motivic spaces in terms of uh, this Navid sheets. Well, so I hope I'm not butchering that name. Have never heard anyone pronounce it, so I'm only doing my best stab here. Uh, so we'll try to define this, and then we'll use this to start and probably not finish talking about trying to get a stable homotopy category. So I don't think we'll complete the construction, but we'll get part of the way there. So I think uh, one thing that well yeah my I don't want to just I mean the text relegates this Nisnevich stuff to like the appendix, and I didn't want to just assume that these are like sites and all this are what people are comfortable with. So roughly the outline for today is first we're going to define sites with a lens uh, uh, yeah with the lens towards uh, like functors of points, and this will be kind of as a quick crash course, and we'll use this to define motivic spaces, and then we'll talk about what the text calls the S stable homotopy category. Okay. Um, so I mean, if what I'm saying is too boring and too elementary, I mean, just speak up and we can move faster or be more whatever. But I I at least before this I had not actually seen this Nisnevich topology. It's not one you usually encounter when you study like algebraic geometry for schemes or stacks or higher things. It's kind of an odd, well, slightly odd. Do you have a question, Krishnendu?
No, I just have a comment. I haven't encountered this earlier either, so you can go slow. No worries.
Okay. Okay. It's yeah. Anyway. So well, without further ado, then let's get started. So the first topic is sites, and so the basic idea is when we talk about like sheaf theories. what we usually do is we need to specify a topology. So in usual topology, what do we do? Well, we specify what open sets are on a fixed topological space or set. I guess not topological space yet. And so the growth and Deeks insight was instead of doing this for a fixed set, you do this for uh, a whole category. And in doing this, uh, you also allow for more than just like open immersions or open subsets of a topological space. And so this is a lot more flexible, and it's a fairly simple notion, but it has a lot of mileage. So the two basic principles here is that we're specifying um, what uh, the open sets are. And I'm going to say open very loosely here. I don't usually think it's anyway. Open sets are for say all of schemes over some fixed x, and in doing so, uh, uh, these open sets are just maps. And or maybe I should say we specify what the let me just modify this. We specify what the coverings are. So instead of looking at open sets, we look at collections of open sets, what we call coverings, and the coverings, or the I guess the open sets in this world are maps, not necessarily say open immersions. Okay, so here's the definition, and I'm not going to give like the most general definition because in the end we really only care about growth unique topologies on the category of schemes and smooth schemes. So we don't need in full flexibility, but this isn't any like we're not really restricting anything here. So what a growth unique topology is going to be a collection. So on say schemes, and in parentheses you can easily replace everything here with I guess just to stick to over S. So you can easily replace everything with for smooth schemes without any problems. So it's going to be a collection uh, of what we are just calling coverings. So it consists of a bunch of maps to a fixed scheme over some indexing set. I guess sorry, that should be like double. So we're going to vary not just what the so T here varies and these vary and pretty much everything here can vary. We're just looking at all, well, we just say that there's a collection. And this set should have some stability. So, well, these are what we're calling coverings. These elements are called coverings. Uh, and they satisfy the following axioms. So the first is that a scheme should cover itself. So covers itself. And so that's if we have an isomorphism of schemes, then the one element set should be a covering. The second property is that we should be able to compose coverings. If you cover, well, yeah, so if we have some covering of T by these TIs, then if we cover each of the TIs, then we should be able to compose these to make it just a big covering of T. So we want this in T, and then some Fij's. Now maybe some J and J. These are all in T, then should be in T. This is coverings compose. And the last property we want is that covering should be stable under base change.
I think you mean if I compose Fij. Otherwise, you don't make sense, right?
Thank you. So it should be stable under base change. So if we have some other map, G from V to T, and covering and then we base change the collection of maps Ti V to V, it should be a covering of B. Okay, so it's not too bad or complicated or anything. I mean, all of these seem like reasonable things. Like, you know, the first is something like, you know, the whole space is an open set. The second one is that a union of open sets is an open set. And the third is, I don't know, like the intersection of, or like this is like the defining property, like a subspace topology. Anyway, it's nothing crazy. But we can get a lot of mileage out of this. So, but before we actually see how we can use this, let's go through a series of important examples.
Yeah, before
And
you move on,
mhm.
in this, is V another covering or what is V? G circle.
V is just a scheme. So if
Oh,
we have a cover of T, and then we should be able to go and base change it. We should like be able to pull back along a
ah,
continuous map to
got it,
cover
got it,
V.
got it, got it, got it,
Yeah.
got it. Yeah.
Okay. So let's see some examples. So the first example that I want to do is sort of like the obvious example, which is an actual topological space. And so the topology for schemes is the Zariski topology. So this is, we're going to just denote this scheme sub Zariski for the big Zariski site. I'm not actually going to define what site is, I guess, but that's fine. Just schemes with a growth and deep topology. And so what we need to do is we need to specify what the Zariski coverings are. So a collection here is a Zariski covering if, well, it's exactly what you expect with one minor caveat is that we don't want these to like literally just be subsets. We want these to be like stable under isomorphism. So these should be, Fi should be open immersions. So we have a collection of like open subsets and they should union to get the whole thing. So the union of their images should be equal to T. Okay, that's not too bad. The next one I want to give is the atoll site. Which we can schemes atoll. And so again, it's more or less the same prototype. We just need to specify what these are. So I'm just going to copy the sort of relevant parts. So an atoll covering, well, we're going to no longer just have open immersions. We're now going to allow for atoll maps. And so, I mean, there's algebraic ways of describing what an atoll map is if this is something you haven't seen, but I think of them most of the time as smooth of relative dimension 0. And you can get plenty of
So
mileage out of
actually,
this.
there is a much easier example here. For each it's not a for each topological space, it could be viewed as a category. then with the topology on it, it is actually a topology.
Yes,
It's a site. That should be,
yeah.
I do feel like that's the first, well, 0th example probably.
Yeah, I mean, I guess I only gave the definition for schemes, so I didn't want to go and
No, like it's like it has to be containing all the things that is previous. So otherwise, it can't be called a topology.
I mean, there's lots of unrelated things that are called similar names. I mean, I agree. I mean, certainly, like a growth and deep topology is literally a generalization of a topology in this sense. But I mean, no, this example just won't be useful for us. Anyway, so the next example I want to give is sort of the most important one, which is this Nisnevich site. And so it's the exact same sort of paradigm as before, although we're going to add one more condition. So well, let me modify it a little bit here. So what is a Nisnevich covering? Well, it's defined to be also an Natal covering. So these Fi is an Natal covering. But it's slightly stronger in that what we're going to ask is that for all field extensions over our let me just schemes this Nisnevich like over a field K, just to, and this is all that's going to be used in the text and is greatly simplified. I mean, it doesn't simplify too much, but it makes this easier for this example at least. And again, it's like only what the book uses. So for all field extensions, what we ask is that that not only is Fi like the collection of those cover, but for all of the field extensions that those points also cover. So we should have that if we look at the image of the F points of GI, then this should also cover G of F. So it's slightly stronger of a constraint. I mean, we'll give a more concrete example. I mean, we'll give a concrete example of a Nisnevich covering or a lack thereof one in just a minute. But and the last one I want to give is not strictly necessary, but probably important in life, which is the smooth site. So it's the same as before, smooth, but now instead of smooth of relative dimension 0, we just allow for smooth in general. So when you talk about topologies,
Sorry.
Yeah.
Before you move on, when you write T of F or Ti of F, what does it mean exactly?
Well, I mean, what I'm saying here is that the images, like when you take the union of the images, you get T, like as underlying like topological spaces. I mean, in that sense. So the Ti of F is saying I'm looking at the F points specifically, and not like so if you work with like characteristic 0 and you're over C, for instance, this doesn't change anything. Everything, like, you're not going to see any sort of weird behavior. The C points like determine everything. But if you were working over something more exotic, then these field extensions capture like things that are not seen on the base field. So you're able to like well, anyway, well, I'll give an example that's more clear in just a minute. But yeah, does that help?
Yeah.
Okay, so the when you talk about topologies, you usually talk about like uh, one topology being coarser than another, and you should already get a feel for like how this should make sense. Like for instance, we saw here that a Nisnevich covering is a tall covering, so Nisnevich is a strictly stronger condition, so this should be coarser than the Atoll topology. So in the order, well, let me use some color here. So on the left, we'll have coarse, and on the right, we'll have fine. And the order in which these kind of go is Zariski, Nisnevich, Atoll, and then smooth. And so in the Zariski topology is the coarsest, the open sets are the biggest. This should be no surprise because the open sets are utterly massive in the Zariski topology, whereas the smooth topology is quite constrained. And overall, you should think of like Atoll and smooth as being closer to like the analytic topology, for example, at least when what it's able to detect topologically. So here's a concrete example, which we'll get some good mileage out of, which is, let's take K to be a field, and then we can construct a covering of the affine line. And so what I'm going to do is look at A1, and I'm just going to remove a point A and just view the like natural inclusion into A1. And then for another point, I'm going to look at well, sorry, for another map, I'm going to take A1 and now remove 0 and map this to A1. But I don't want this to be the inclusion map. I want this to be the map that takes X to X to the N. So it's, I mean, clearly each of these maps are smooth of relative dimension 0. So this is an Atoll covering of the affine line. And the question is, when is it Nisnevich? And what we need is that it actually on points it should be a covering. And what that means here, and we can just translate this to the world of rings. So what we want is the only potential problem here is going to be this where we remove A and 0. And so the question is, well, 0 is obviously going to be picked up here, but the question is the image of A going to be picked up there? And that's the sort of the crucial thing. And so this will only happen. So the answer is only Nisnevich when the equation x to the n equals a has a solution over k. If it doesn't have a solution over k, then we can just well, then those points will fail to be yeah, we'll fail to get the surjectivity condition we want.
Yeah, to repeat it is to make sure that I'm understanding what you're saying, you're trying to check the second condition of being Nisnevich is true. And for that you need to make sure that under their images, they if you take the union gives you the A1, right? Is that the thing?
Yeah, so we need to check with we need to check on the like F points, right? And so like what the F points are in this case is just I mean the F points are literally like F minus A sitting inside of F, and then F minus 0 sitting inside of F. And F here under the F points is again just this map that takes x to the n. And so we're asking, when is this, like, when is their solution, like when is A hit by F, or yeah, by this map F here, right? Because that's the only point that we need to have covered. Everything else is just kind of covered trivially by I. And so we need to have this
Right,
point
right. You
A
are trying
covered.
to hit A by F. Right, right, right.
Yeah, so we need a solution
Mm-hmm.
to this.
Sincere. Thank you.
Okay. Anyway, so it's a very like it's a fairly mild constraint. Like and in fact, it's not like clear to me why one prefers, like, I guess it's slightly coarser, and that might be good in some ways, but like I don't see why you don't just use a tall the Atoll topology instead. But yeah, so maybe there's an expert can chime in about why this is the sort of right topology one should use. But anyway, it's one we will use. So okay, so let's now use this to, well, yeah, I guess this is sort of like an interlude. So we've defined topologies, and the reason for wanting to introduce this is because we want to talk about like sheaves with respect to these topologies. So what does it mean to be a sheaf with respect to a Grothendieck topology? So let's take T to be a Grothendieck topology on schemes. So a functor, or I mean a pre-sheaf to sets is a sheaf with respect to T. Well, it's exactly what it is if we were working with topological spaces, and like using this an example that Guan explained. I mean, you can literally just like sort of copy the sheaf condition. So you should have like uh, uh, gluing and local identity, and so this is can be expressed in a sort of convenient way. So we're asking that for all the coverings in our Grothendieck topology, we should have a co-equalizer, sorry, just an equalizer. Getting ahead of myself. Oh. And I mean, if you prefer the sort of classical sheaf description with like asking that you have gluings of sections and all that, like you can, I mean, all this data is encoded here, but you can, I mean, make this like, I mean, one thing you can do is you can sort of write this out as a pullback square. And so what product? What you should think is that like this these open sets here are like intersections. So we're starting with collections on both sides here, and we're asking that they map to something and where they agree on the intersections. And so the fact this is a pullback is asking that you can glue and that the gluing is unique, which is exactly the sheaf property. So this is
Wait, you can't always write equalizers as pullback, right? Like, is it obvious in this case?
uh No, I mean, this is true for sets. So I mean, this is
Okay. Oh, I see.
fine, but
I see.
yeah,
I
I
see.
mean, you should be, yeah, I mean, you should be careful of these things for sure. Okay, so where to next? We have growth and weak topology on the category scheme. So in theory, we should, and we have like now sheaves. So what should we use this for? Well, the beautiful thing, and this is like has motivated so much algebraic geometry, is this notion of a representable functor. And so what we can do is we have for every scheme, we have a functor that takes us from schemes up to just sets. And what it does is it just takes a scheme and uses the Hom space functor or Hom set functor. And so this is I mean, very simple to describe. So this automatically gives you a pre-sheaf. And by definition, this is a pre-sheaf on schemes. And what Yoneda's lemma tells you is that like understanding these representable understanding these functors is enough to understand like the category of schemes. And so this is like a really rich area. And so the kind of a question or a thing in algebraic geometry then is that if you have an arbitrary pre-sheaf, so if F is an arbitrary pre-sheaf, when is F equivalent or isomorphic as a pre-sheaf to some Ajax, right? To coming from a scheme, and well, the part of the answer to this, so a partial answer, and really the hard part is if X is a scheme, then it's automatically a Zariski sheaf. In fact, it's so this is very non-trivial. It's actually a smooth sheaf as well, and in fact more than that. I mean, I didn't do things like FPPF or FPQC, but it's it's a very nice sheaf. It very well behaved. So what's the takeaway is that like schemes themselves can be thought of as like Zariski sheaves, maybe with some extra conditions. And in general, we can look at, I mean, a lot of algebraic geometry starts by taking some site and then looking at sheaves with respect to that site and calling them some notion, right? Like if we do this with the tall sheaves and kind of give similar criteria, then we get like algebraic spaces. And anyway, so we can do things of that flavor. And I guess, morally, if we do this like with FPPF and we upgrade like sets to maybe like groupoids, then we can get like, stacks and all of that. Anyway, that's like a quick overview of sites and like what we'll need. Is there any questions before we go and go back to motivic spaces?
No, you said that you won't say what a site is, but how should I think of them? Like, it's
All a site is category with growth unique topology.
okay, got it.
Yeah, you won't lose any. Yeah, that's all I mean. Okay. So let's move on to motivic spaces. So I want to give a new definition, and I mean this is a different definition. They're like model equivalent or whatever, but this is a different definition than what Guan Yu gave. And for all of this, I think we're doing S to be spec K. So if you want to do more than this, you have to make sense of Nisnevich, and I think there's some like headaches. And anyway, for now, I think that's all we're gonna do. And then I don't know, maybe if we run out of material, we'll go and do more general stuff in future talks or something. But what I want to do then is define this category of spaces, which we're going to denote SPC of K. And this is going to be the category of Nisnevich sheaves, which are taking values in simplicial sets. So it's I didn't I replace everything that we had before for set with simplicial set, and I mean there's no problem. That doesn't affect the sheaf condition. And so the components of this is this S means simplicial set valued, and here we're talking about the full subcategory of smooth schemes rather than just like all schemes. Okay, so here's the two most important examples of Nisnevich sheaves. So the first one is, well, what I said before, if we have a smooth scheme, then we can view X as a sheaf with respect to, well, the Zariski topology, but if you recall, I also said the smooth topology. In particular, from this diagram of coarseness we did, it's also going to be a sheaf with respect to the Nisnevich topology. And so what that means is we can view X as one of these Nisnevich sheaves, I guess I should say a motivic space. And just by like saying like using like the free functor from like sets, the simplicial sets.
Yeah, so I have okay, first of all, how do you view this as Nisnevich with respect to Nisnevich topology?
So it's, do you agree that we can view it as a Zariski sheaf?
Um,
So
no.
maybe I should write like H sub X.
Oh, I see.
Yeah, I mean it's like by Unadas, like you really should just think of this as being X itself.
I
But
see.
yeah,
So
so
by
we
this, okay. I see. Okay, this is a Zariski set. That is true, and
so it's a
Zariski.
Zariski sheaf, but it ends up being more than that. It's actually like for I mean it's for schemes, they end up being sheaves for like Atal, for smooth, for FPPF, FPQC, and so like all of these are finer than Nisnevich, and so it's automatically going to be one for Nisnevich as well.
I see what you mean. And when you say is sheaves Nisnevich, do you mean that sheaves are? I mean,
I
they're
mean this
landing
is
in.
free sheaves. This is a subcategory of free sheaves
Yeah,
um, on smooth schemes, which
in
is landing
simplicial
in
sets.
simplicial sets.
That's it. It's not enriched over simplicial sets or anything. Uh,
Uh, I mean, what do you mean enrich?
like home set being a simplicial set, do you expect that home to be also a simplicial set?
Uh, well, I mean, I mean, no. I mean, there is an internal hom, and it's like enriched in sheaves, right?
Okay.
Like this. I mean, this is like a sheaf hom, right?
Mm-hmm. Mm-hmm.
I think. Oh, well, I'm sorry. No, that's wrong. We need like simplicial abelian groups or something instead then. But anyway, no, I just mean like, yeah. I mean, what I mean is just this.
Is that thing? Okay.
Yeah.
Okay. No worries.
Okay. So this is the first example is that we can regard any smooth scheme as a Nisnevich sheaf, and the second key example is if we have a simplicial set. Well, we can define a pre-sheaf called the constant pre-sheaf. And all this does is it takes one of these schemes and spits out our simplicial set. Oh, sorry, this is awful notation. I apologize. What's a good notation for a simplicial set? Upside down triangle. Anyway. Okay. So we can take a smooth scheme and just like do the constant thing. This of course like this is not like this usually fails to be a sheaf, but we can like sheafify. So we can apply sheafification to get something that's deserving of the name the constant sheaf. So in the same way that you would for classical sheaf theory. This is the constant sheaf. Okay. So what have we done? Well, there's sort of two different worlds in which we can view this Nisnevich sheaves in like the tautological sense. There's a way that we can view any scheme as a Nisnevich sheaf, and then there's also a way where we can view any simplicial set as one. So we've now kind of created this world in which both schemes and simplicial sets live together in some version of harmony. And so this is good. This is kind of like what we would want from like a category of motivic spaces. So I think this is a good start. And so what's but yeah, anyway, but before we like get into some more particular aspects of this, I want to also make mention of the sort of pointed version that's quite important. So we have pointed this is a category of pointed spaces. And so I mean it's just going to be consist of sort of like pairs x and some map from x that goes from spec k. So we're just looking at pairs of x with a point on x, and this is I don't know like exactly how you would do it like for topological space or whatever, like just obvious thing. And like of course like the map should take base point to base point, whatever. Okay, so we have this category, and the category of pointed spaces is nicer because well we can make it into a symmetric monoidal category by pointwise wedge product. So let me write this down. So we can simplicial set, pointed simplicial set has a wedge product. So it has a symmetric monoidal structure, which we call this wedge. And so we can do this pointwise on
I think
pre-sheaves
we
and
call
then
it just smash. Like
oh sorry. I just have these flipped up in my head, right?
yeah. Yeah, never mind. Yeah.
Yeah, smash product. Yeah, my bad.
We can call it tensor. Like
No, smash
so
product is correct.
all the solution of all the problems.
Yeah, anyway, smash product. Thank you. And so what we can do is, like, if we have two pointed spaces, and I'm just gonna like habitually ignore that they have, like, I mean, obviously they have a point and it's like canonical, whatever. Like, anyway, so what we can do then is give a definition of the wedge here at the level of pre-sheaves. And so when we plug in a scheme, well, it's just going to be pointwise. So we're saying YT, and then we can sheafify to produce a product in pointed spaces. So this is the pointwise product in Nisnevich, or pointed spaces. This is sheafify. Okay, and the sort of corollary of this, which, obviously there's work, but this is not too bad, is that this is a closed symmetric monoidal category. Okay, and now I can go back to what I was fumbling about with Crescendo earlier, which is this category is closed until you have an internal hum, so it's enriched over itself. Yeah.
Oh, okay. But how do you define the internal home? Like,
I mean, it's like a representability thing, right? Like, and
thing that represents the tensor.
it's closed, so anyway,
Okay.
you can do it in the same way that you would define it for sheaves over like abelian, with valued in abelian groups,
Uh,
or like pointed simplicial sets is also enriched over itself, right?
yeah.
So you can copy this definition, like, and instead of like, like, you can do things like x y
Mm-hmm.
valued in t, and actually I feel like this is I mean, this might be correct. I'm going off book here though, um, so again, this should be like the pre-sheaf version. So it should be like hom internal hom here,
Right. That's
something like this seems actually wrong in some sense, but anyway, so this is like, maybe this is correct. Anyway, like, I seem to remember for like ordinary sheaves, like, this is wrong. Like, you'd want to look at like restrictions. Uh but anyway, well, anyway, grain of salt. Yeah, I mean, this is probably wrong. Because I think for normal sheaves, you want to look at like x restricted to t or something instead. So anyway, well, anyway, okay. So what? Anyway, yeah. So the last thing I want to say before finishing up with trying to get towards the stable category is that there's two really important objects that we want to care about, right? So in the world of homotopy theory, you care about circles, and homotopy theorists love motivic spaces because they don't have just one circle, but they have two circles, and homotopy theorists love circles. So that's why these are studied. No other. No. So there's two circles, and this should make sense because we have combined the worlds of schemes, which has its own circle, and the world of simplicial sets, which has its own circle. So we have the simplicial circle, which we're going to denote S1 sub S. And if you recall, this is just this coequalizer we're just taking an interval and gluing a point. And from this, we can also do things like define the simplicial spheres by taking what smash products of simplicial circles. And so this is one circle. The other circle is sort of the one that comes from algebraic geometry, and this is the Tate circle. So S1 sub T, and this was simply just GM, right? This is our multiplicative group that we're viewing as a not just a scheme, but as a Nisnevich sheaf under this like description we gave before. And likewise, like we view this as a Nisnevich sheaf via the constant sheaf description we gave before. And so the likewise we can do things like create what's called Tate sphere by taking wedges. And we can also do like combinations of this, like we could take wedges of some circles and wedges of some spheres, sorry, some circle simplicial and some Tate, and create some mixed circles. And this is roughly what Guanyu was doing last time when we looked at this like simplicial circle wedge with GM we were doing anyway. But well, yeah. So what we need to do then is like we're trying to build, like we have this category of motivic spaces, and we want to go and develop like a stable homotopy category. So the yeah, so this is this last part. So this is this S stable homotopy category. So we're not quite to the point where we can actually get the full stable homotopy category. And the problem is like we need to we need a combination of like simplicial circle inversion as well as the Tate circle inversion. And we just I mean, this is a lot to do in one day, and it's actually a lot to do in like, I don't know, 5-10 minutes, whatever I've left. And so I think the goal for, well, what we're going to try to do today is just do just do the S1S inversion. Okay. And then next time I think we'll probably finish this and actually get to the nice stable homotopy category where we can actually do cohomology and do all the fun motivic stuff. So let's well we have we have this circle, and like it has this flavor of being like a spectrum, because it's, we can take its iterated smash products and we get these spheres, and it's like, okay, this is looking like we're doing ordinary homotopy theory, so this is good. So we just need to now adapt some of this into this simplicial space world. So here's a definition. An S spectrum E is going to be a sequence of pointed spaces En indexed by the non-negative integers with structure maps well, it should be yeah, it's sort of the obvious things. Such that the obvious things also commute. So such that if you what do I want to say? No, sorry. I don't think I need the meeting yet. Okay. We see structure maps. That
Yeah, I think you are trying to say the morphism between two.
yeah, okay. Sorry, I'm just okay. So we have the structure maps, and so then a morphism from say E to E prime of S spectra is a collection of maps En to En prime such that the obvious diagram commutes now. Okay. And the resulting category, so we're gonna write SPT sub S to refer to the category of S spectra. Okay. And the only example we're going to provide of this for now is the tautological one, or yeah, which is the sphere spectrum, simplicial sphere spectrum, because now we have two. So this is the nth term is the nth simplicial sphere wedged with X. Kind of like the obvious thing. Okay. Probably a good time to quick ask for questions before we talk about some homotopy. Okay. How much time do I have left? Is it 4:15? Is that when we stop, or
Yeah, I mean, you can keep going. Yeah.
what time am I supposed to stop though?
Yeah, I mean, officially 4:15, but
Okay, I'll go till 4:15 then. If that's the official point, we'll go till then.
okay.
Okay. So we have spectra, and now we want to start talking about like homotopy. So let's uh let's start with let's take a pointed space, and what I want to do is define like its homotopy uh, groups. And so what all I'm going to do is just define this like pointwise. So define a pre-sheaf. Again, this is like all like everything we're doing right now is just on the simplicial side. So it's pretty much just everything we did for simplicity. It's like spectra, homotopy groups, all of this. We're just doing pointwise to this category of Nisnevich sheaves and like producing something. And it's only part of the story. Like we will also need to do the actual algebraic geometry part, and we need to make them compatible in nice ways. And this will be a lot of non-trivial effort. But okay, so let's define a pre-sheaf, and it's going to be pi sub n of x, and it's going to go from, well, it's a pre-sheaf on smooth schemes, but this time to sets and not simplicial sets. And what it does is it takes T and it spits out the nth homotopy group or nth homotopy object of x of t. So x of t is a simplicial set, so we can look at it that. And I'm just going to write x. Yeah, I mean, this is the notation of the book. I don't particularly like this notation, but I couldn't find figure out a better one. So this is we're just viewing X as being I mean, this is like the image of X in X of T.
Yeah, but
And so,
isn't this supposed to be abelian group?
well, no, I mean, this is not true for like, I mean, most of the time, no, right? Like, it's only going to be a abelian group for n greater than or equal to 2.
Yeah, okay, then how do you define pi minus 1, suppose?
No,
Uh,
no, no. Sorry. Okay. Define a pre-sheaf. Say n is greater than or equal to 0.
okay, never mind, go ahead. Yeah.
Okay. Yeah. It's like anyway. Uh. Or yeah. I think it's fine. So what Christian is saying is true though. Like if you have n greater than equal to 2, well, uh, pi n of x. Well, this is uh sheaf in abelian groups, and I guess more generally I should say, um, like this is an Nisnevich sheaf in general. So this is a Nisnevich sheaf, just not necessarily valued in abelian groups. But when the pointwise behavior is abelian groups, then you get that value in abelian groups.
Yeah, and
And
yeah, before you continue, and I think to define that pi-n for simplicial sets, you have to apply that EX cons EX infinity functor, right? Otherwise, there is no guarantee that you are getting xt as a vibrant object always, isn't it? I think that's the
yeah,
way the book defined in the beginning.
yeah. So I mean, I think like taking. I mean, you can always just take like the geometric realization and like
Yeah,
look at
on
that
that. Yep,
yeah,
on that.
look at that homotopy. I I don't think I can't actually remember how much of the higher homotopy groups we talked about for simplicial sets.
I talked about it, and in the book, if I remember it correctly, I mean, I talked about that, to define these, you need to use Kant's CX infinity functor, and it's the same as computing the actual homotopy groups of the geometry realized
Okay.
in simplicial
Hmm.
set. So I guess it's in that sense. Hopefully,
Yeah, yeah. No, I mean it's certainly like I certainly this is what we want to write down. How you actually prescribe like high end to maybe a general simplicial set is like in a internal to simplicial sets might be like slightly tedious or whatever, but uh, we do want it to be valued in all simplicial sets. Like we don't want to just restrict to the fiber.
right, right.
Yeah. And it's definitely the case that this may fail to produce a fibrant object, right? Like just take something that's not fibrant and look at the constant sheaf.
Yep.
Okay. So we have these things and of course these like pi n's define a functor that take us from pointed spaces to these ordinary Nisnevich sheaves. Okay. Um, so this allows us to make sense of uh, like weak equivalences now. So we can define um, so a map between two S spectra is an S stable weak equivalence well, you can probably just guess at this point, but if it induces an isomorphism on phi n's for all n. And this should be like an isomorphism of sheaves, right? Like, yeah. Good. Okay. So I knew, at least I was roughly aware I'd be in this position, and knew that I definitely would not have time to talk about like giving this a model structure, but it can be done, right? Like, and this is the content of one of the appendices, is we can actually give this a model structure, this category of S spectra, such that these are actually the weak equivalences. And so the reason I say this is because I want to explain what this stable category is, and it requires us to localize at these or invert these weak equivalences, and to make that precise, we should be using like model theory. But so we can define this to be the localization of our category of S spectra at well, S stable weak equivalences. And this is called the stable S stable homotopy category. Okay. And the what do I want to say? Okay. So if we like, how does this relate with just the world of simplicial sets? So we have a functor from simplicial sets to our category of, sorry, I should say, we have a functor from simplicial sets to our category of, sorry, pointed simplicial sets to our category of pointed spaces, which is this constant sheaf functor. This is the constant sheaf functor. And what you can quickly convince yourself of is that this takes these, it takes the spectra here to these S spectra here. Right, and so this induces a functor at this level. And it's also not hard to convince yourself that like this this functor takes the weak equivalences to these S stable ones, or you know, like it takes all the fibrants of fibrants and whatever else in like the model sense, and so it induces a functor at the level of stable homotopy. Okay, so we've kind of enlarged this ordinary stable homotopy category for simplicial sets to to include like some algebraic geometry, but the algebraic geometry is not really playing a role yet. And so what we need to do in order to actually make the algebraic geometry play a role is to like, well, like what the whole point of doing like motivic stuff is you want to make A1, or not the whole point, but like a huge part of this is like we want to make A1 contractible. So we have a notion of homotopy now, and so it's like, can we, make A1 actually an invariant in this stable homotopy category? And this can be done by just like, I don't know, brute force or something. I mean, it's like, or just like willing it into existence. So if we have a spectra, it's going to be called A1 local if for all U smooth and N and Z, the projection from U cross with A1 just to U and induces a bijection for Hom spaces here. Okay, so I'm writing notation I haven't wrote before. So bear with me as I just try to get this written down. Oh, wait, what did okay. So here is just like the at a point space. And this is like suspension, simplicial suspension, where we wedge at times. And I wrote what these are before, but this is the sphere, simplicial sphere spectrum. Okay. So we should get an induced map. And this should say that like the Homs don't see the difference between if we added a bunch of A1s. So I guess that's good. And so then in general, like what should an A1 stable map of be? So a map E prime of S spectra is an A1 stable weak equivalence if the induced map is an isomorphism for all local. Okay. And so the lemma that's sort of the I mean, yeah, this is some formal process that you can do to make A1 contractible. I mean, that's maybe the takeaway for the minute I've already gone over. But the key takeaway is that just the ordinary projection is A1 stable weak equivalence. And so this implies that we have contractibility. And so we can localize our well, we can localize S spectra to get the A1 invariant or A1 stable S homocode. I'm getting caught up words, but anyway, you can localize to get the A1 inversion as well. So I definitely was rushing a little at the end. So hopefully next time whoever speaks can maybe review some of this. But yeah, I think that's all.